Of notes?
Yes.
Why?
I don't want to write that down.
All that garbage there.
Yeah.
You didn't write it down on Wednesday? Or were you not here on Wednesday, Walter?
No, I wrote like 6 of the eyes, but I didn't get the whole long.
Well, because you're supposed to be. You don't use skeleton notes.
No.
It's
don't
on
have
you,
notes
man.
on.
It's on you. I'm not. I gave you all these. You every time you jot down everything that's on there. That explains a few things.
It's how you write it down, you say it in your head, you write it down.
Yeah, but you're writing down the stuff that I'm writing down. How many people don't use skeleton notes? Oh, you dumbass. I put some time into it. How many use the skeleton notes?
I don't
The rest
know.
of you,
They
yeah.
have iPads, that's not fair.
Yeah.
I just upload, I have to go print the thing.
Oh yeah, that would take
No,
minutes.
it's-
Minutes. At the beginning of the semester. All right, so I mean, you honestly might want to print these ones out because even like, when we get to the moment equations, right? Like you don't have time to write all that down. You're gonna make a mistake along the way and stuff.
Yeah.
Right.
Alright, I'll print
So then in 2D, this HG, right? It was the integral of RdM as seen from G crossed with omega crossed with RdM as seen from G dm, right? In 2D, omega was just in the k direction, R was in the x and the y, which then led to this momentum just being I times omega. R squared dA or dm rather is the moment of inertia, right? But when the direction is in the x, y, and z direction, and your rotations are in the x, y, z direction, this thing blows up, and it becomes what we see right there. And then you can write this thing in matrix notation, okay? And that's the matrix notation of that inertia tensor, right? Down the diagonal are our moments of inertia. That's the resistance to rotation about their own axes. And then the off-diagonal terms are what we call products of inertia, and it's what links motion around one axis with momentum about the other axis, which is really weird to think about, that if it's rotating this way, it's causing momentum in one of the other directions, right? And the only way that that would happen is if it's imbalanced, right? If it's lacking some symmetry, if it's something that's odd, right? What I used as an example on Wednesday would be a tire, right? You got a tire that might be imbalanced, like going this direction, right? So it has too much weight on one side like this, so it goes around and then it's off. So what they do is they put these little weights on the tire to make it even, so that it's balanced going this way. But if it's unbalanced going this way, you pick up a side-to-side wiggle, right? And you'll feel it in your vehicle. Your steering wheel will rock back and forth. And it's because it's unbalanced this way, but it's causing momentum this way, and it's because there's a product of inertia. There's lacking some symmetry, and there's a product of inertia. These off-diagonal terms, right? It's in the off-diagonal terms here, right? That's what links it, right? Remember the way this works. I go that times this, this times this, this times this, right? And then that would give me the momentum around the x-axis, and you could see that omega y gets multiplied by this product of inertia, and it would cause momentum about the x-axis. So the off-diagonal terms are that. If you can get this thing in an orientation, right, or if it's perfectly balanced, then you don't have to worry about it, right? And we're gonna aim for that. We wanna find symmetry in our structure because it makes the problem way easier to solve, because all these off-diagonal terms go to 0, right? And then all you're left with is the diagonal terms, okay? And so most of our problems, we're gonna have symmetry. And we can go that way. We'll go that way. What's really neat about it is, remember I think it's neat, mechanics and materials, when you have stresses and you can orient your little block in such a way that you don't have any shear stresses, all you have is normal stresses. What's that called? Principal stresses, right? You principal direction, principal stresses. You can do the same thing with these as well. They have like a principal direction for your moments of inertia. You can orient it in such a way that you only have moments of inertia, no products of inertia. And you find them the same way. But we're not going to do that. We're just going to deal with things that are symmetric, right? The type of symmetry. So just real quick, you can calculate. This is how you calculate them. That's the moments of inertia, and here's your products of inertia. This is how they get calculated. Good news is we don't actually have to carry out those integrals. There they are, right? They're provided in the textbook, right? The moments of inertia and products of inertia, right? We use these things. Well, we've seen these before, but we were just after IZ, right? That's all we cared about before was IZ. But now we have, we care about the other ones as well, the IX, the IY, and the IZ, right? And so they're all kind of pre-calced for us, right? You can find all of them in there. These are all the products of inertia and moments of inertia, okay? The products of inertia, you notice if we have something that's very symmetric, right? So this is, guys, is symmetric. So I've got symmetry. So if I've got this plate right here and I'm looking around, it's the very center of it, then I have symmetry about all my axes, right? What I mean by symmetry, I mean if I cut it on the y prime z prime axis, right? Cut it through there, there's a mirror on both sides, right? If I cut it right down this thing, oh, what's it doing to me? If I cut it right here, right? Sliced it through there, this side cancels out that side, right? If I cut it through this z x-axis, the stuff above is the same as the stuff below, right? And if I cut it, one more. Yeah, if I sliced it lengthwise like this, then it's canceled off on either side. And so you see that about the center, all my products of inertia are zero. They're giving those things as being zero. But if I cut it down here, if I'm doing it about this axis down here on this corner, there isn't symmetry around some of those axes, right? There is, if I was looking about this plane, the YZ plane right here, right? There isn't something on this side to cancel this side out, so I would pick up a product of inertia, right? And so my product of inertia ends up being something because it's not balanced about if it was rotating about that other axis, right? So you're always looking for symmetry. If you can find symmetry, it'd be great. This thing, anything that has rotational symmetry, what rotational symmetry is if I drew a little rectangle, right, and I rotate it about that axis, I get that shape. And if you get something like that where you have some rotational symmetry, symmetry about an axis where if you rotate it around, all of your products of inertia go to zero, right? So there you can see all of my products of inertia go to zero. Right, same thing with this guy here, and then some other more advanced shapes down here. They give you all of those things. And again, anything that you find that's really symmetric, you'll notice that all of our products of inertia go to zero. But there's going to be some cases where they're not zero. And in the book, a lot of times we just give those to you, right? You can also calculate them, right? If for some reason you have to build up your product of inertia or your moment of inertia, you could use the parallel axis theorem. So that's what this is about, is this parallel axis theorem, okay? So let's just write one thing. I'd lie. Oh, no, I'm not going to lie to you. We won't write anything down, okay? We won't do it, okay? So then now we're set, right? Where we're going to head, and this is, Walter, this is why I want you to print these things out, right? This is, you don't want to write this down. That's a lot of stuff, okay? So now we have that moment of inertia. Literally what happens, right, when we need our equations of motion, right? We're trying to do F equals ma, right? Here's my force equation. Force is equal to mass times acceleration. So you get 3 of these equations. And then I also get 3 moment equations because I have rotations about the x, y, and the z direction, okay? If I take this definition of what hg is and I substitute it into this over here, this thing blows up and it becomes this. These are Euler's moment equations, right? Right, that's what we're going to have to use. So when we do this, we sum the force in the x, y, and z, and they're equal to accelerations. We write down our 3 moment equations. Those are our 3 moment equations, right? It used to just be I times alpha. Now it's this son of a bitch, okay? What's really nice though, right, is if we are in the principal frame, meaning that we don't have any products of inertia, all these go away, right? But what's really nice, I mean, that gets us there, right? That leaves us with this, right? That's what's written down here. These are the same. It's better, but it's still not perfect, right? There's still a lot going on, okay? And again, what we're trying to find, right, is when we had that little fidget spinner and we were rotating that sucker around, you know, we felt that other moment. Well, we need to figure out what that moment needs to be in order to hold it in place. And this is how you do it. These are the moment equations that you have to use for it, right? And I don't trust you writing these down, Walter, really quickly. So just print out these 2 pages. Okay? And the rest of you guys do it too. Okay. And then you could also do the same thing. These are the same moment equations, but just written in matrix notation. And so when we do, and then, I mean, so that on Monday, right, we're down to 3 days, right, after today. On Monday, after you've given up on college, right? You're at home and you're just like, this is awesome. Then you got to come back for like this intensity. This is worth 30%, right? The finals were 30. Yeah. right? Yeah, that's a lot. That's a lot, right? We'll go over a solution procedure, and then we're just going to dive in. So on Monday, we'll do a little bit of cover of that, and then we're going to do this example, and then I'll show you how you could do it in MATLAB if you wanted to. Then we'll do this example, and then I think the next one is the grand finale. They take a while to do is this guy, and this is really similar to the problem we started out the semester with, where we had that wheel spinning, and I hung it by one axis, and it didn't fall down. It actually just rotated around slowly. This is that same problem. And so by the end, we'll be able to solve this one problem, okay? We'll be able to figure out how it rotates about. That's where we're headed. All right.
We might as well start one of them.
No, we're gonna do a Kahoot. Remember? I always want to do more of these because they are pretty fun. I don't know what you guys think of them, but I think that they're fun. Okay.
I like it for extra credit.
Yeah, extra credit. All right, you guys, you know how to do this, right? You can scan that code, or you can type in the game pin. Put in your real name, because I think I have access to who did it, right? And so then I can go through and add that extra credit for this. And if you have a common name, make sure you put last name too.
My last name's too long.
Yeah. But you're the only Walter.
Yeah.
You're the only Walter. Do they automatically sign? Do they automatically sign those?
Well, we can change it.
Oh.
I'm doing
I'll also say this, right? I also could see if you're participating, so you have to participate too. You can't just put your name in and then kick back. Like you have to at least hit the answers. Yeah, I don't care if they're the wrong answers, but you gotta do it. Is everybody in? Everybody in? Anybody not in? Get in. I'm gonna hit start. Everybody good? Why doesn't anybody respond? Okay. Anybody not in? All right, here we go. Okay. So this is 3D kinematics. It's the 3D kinematic. Remember I showed you that little top thing, and I said you're gonna see this again. Here it is. You're gonna see it. Okay. So it's just gonna start asking you little questions. We're gonna start out easier and work our way up. So you might get a piece of scratch paper out if you want, right? Or you could rely on your, even though I tell you never rely on your intuition, here, for the speed, you might have to do some intuition. And nobody's done this problem, right? See, last year I had the problem, I did it, and somebody had done the problem, and they had all the answers there, and then they're like, well, I did it for fun, and then they just cranked it out really quick. Okay.
Wait, we're doing actual problems?
Yes, this is a problem out of the book.
3D kinematics?
3D kinematics, we had true or false. Okay, so the outside frame is the body and the disk is the secondary reference frame. So you gotta look at the picture first, right? The outside frame is the body and the disk is the secondary reference frame. True or false? 10 seconds, 9 seconds. Ooh, I got 15 of you. Okay, right? Well, I don't have that thing. I don't want to go to the next problem. But in that case, right, remember I said sometimes the body can be the thing that's inside the other thing that's rotating, right? So it's that thing on the inside is rotating relative to the thing that's rotating, right? So it's not rotating about it, it's rotating within it. But the body is actually the disk that's on the inside because it's the thing that's rotating within the other thing that's rotating, okay? All right. We got Hunter. Hunter in the lead. Who's Hunter? Good job, Hunter. Chase. Who's Chase? Chase. All right. There you go. These are the names I should have learned, right? Derek. Hell yeah, right there in third. Jacob. What? Walter, where the hell are you, man?
Third.
Right.
I'm 13 points behind Aiden.
Okay. Here we go. What is the angular velocity of the disk? You see your intuition here. You're out, Walter. You're out, dude.
That was fun while it lasted.
Ah, shit.
Yeah. Oh, I did it right. Got cooked on that.
You know, you got both of them, right? You got the rotation of the body relative to the secondary reference frame, and then you have to add on to it the rotation of the secondary reference frame, right? So yeah, by the way, these are in vector notation. If you haven't been able to pick this up, right? That's the I, J, and the K direction. Okay. Right. So it was 10 around one axis and 2 around the other, and then you have to add the 2 together. So you get both of those, right? Because it's the body, it rotates both things. Oh, actually, I could do this, right? I could show it. Yeah, right. So it's got the omega in the y direction, 2 in the y direction, and then it has 10 in the z direction. You just add the 2 together, right?
That was acceleration when I had it.
Okay. Here we go. See how we're sitting here? Ooh, Hunter's still at the top. Hunter. Right, Jacob, you're still up there. Zach, you're gone, man. Or Derek, you're gone, man. Zach, you're in. Who's Zach? Zach? Oh, right here, right here. Zach. Matt, who's Matt? Matt? Wesley? There you go. Good job, Wesley. All right, here we go. What is the velocity at the center of the disk?
Oh shit!
Yeah, is that good? Is that a good one?
Are you kidding me?
That's a good one. Yeah, that's a good one. I got you. I got you. Oh man, those units, those units got you. That was designed, by the way. I designed that sucker. Right? Right? The velocity is in millimeters per second, right? The angular velocity is in radians per second. Right? You were working your way through and you saw the first 0, 0, 0, and you're like, I got it. But
I knew it was 0. I looked at the first one.
I know. It was by design. I was after you. Right? See what we're doing here. Oh yeah, Hunter just pulling away, man. Just pulling away. Zach gained on you though. Who's Zach again? Zach, all right. Jacob. Jacob, who's Jacob? Oh, Jacob. Nice to meet you, Jacob. Wesley again. Where's Wesley again? I'm learning new names. Last week. Oh yeah, Wesley. And Carver, you're new. You're new on the thing. There you go, Carver. All right. Still no Walter. Can I see the rest? I want to see where Walter really is. All right. What's the velocity of point A? I got units on there again. Walter, have you even gotten one right yet? You got the first one right. There you go.
And then I forgot K cross the K.
Wow, guys. Right? So this is what I'm saying. You can get away with it, right? And for this type of problem, like intuition should help you a little bit, right? Because this thing, right? It's rotating. I'm after point A over here, right? So it only has one rotation, and that's 2 radians per second, right? So it's just rotating this way, and it's coming out, right? It's coming out, and out is the positive. Right, coming out right this is the positive x direction. I think it was the only one that had in that thing. It was the only thing that had the positive x direction, right? I think one of the answers only had it. But then also the radius would be 40 millimeters, and then times 2 would be 80. So that's going 80 in the positive x, right? So try to just like try to do a little deductive, right? You're limited in time, so you got to do a little deductive reasoning and work your way through, right? Does everybody see that? That why that's going to be there? I see. 6 people got that. That's how, what's that?
How similar are these multiple choices compared to
Or 21 got it right. Sorry, I wasn't listening, Mark. Yeah. It looked at, I was nodding, and it appeared as though I was listening.
How similar are these multiple choices to the exam?
Not at all.
No.
Yeah, not at all. Not at all. Yeah. Completely irrelevant. This is, yeah. They're just, I'm asking, mostly, it's not like numerical problems for the exam. It's like, sum of the forces equal what? And then just have like, and then I have like multiple choice of what they're equal to. Maybe not that easy, but you know what I'm saying? Like, force equals mass times acceleration. It could be that one. Maybe I'll throw that one in there for you, right? Okay, so 21 of you got it right. All right, let's see where we're sitting here. Oh shit, Hunter, you're gone. What happened? It's just completely wiped. And Zach, got you there. You didn't do the problem, did you, Zach? You didn't do that. All right, good for you. You look a little untrustworthy over there. Jacob. Again, who's Jacob? Oh, you're Jacob. Wesley. All right, Wesley. Rex. Shit, I didn't even know we had a Rex in here. I should have learned your name. Celine. Oh yeah. You copying off Wesley? Yeah. Whatever works. All right. Double points.
Oh, I was already thinking about this.
Yeah.
Right, man.
That's a hard one. You got a little extra time if you want to make sure you get it.
Oh.
Should I make it that you have to get at least 2 right, Walter? Should I just... You have to get at least 2 right. You get extra credit. Yeah. But which one though, right? You get it? judgment, yeah. Right after I said, just like use your intuition, you could go like, which direction is it moving? Well, you can look at it and see it's going to be a negative, positive, negative, right? Well, was it this negative, positive, negative, or that negative, positive?
How's it in the negative?
Right? It's spinning this way, right? It's spinning this way, so it's on its way. It's on its way back. Okay? Right? Yeah, it's on that. So it's on its way back, right? It's going that way, and then, right? And it's going that way, right? So negative, positive, negative, right? And then just maybe do a quick little math and see what the magnitude would need to be, right? There we go. How we sitting here? Any change up? Ooh. Nice. All right. This is really embarrassing. I forgot who Jacob was again. Who's Jacob again? Jacob. God, my bad, dude. And then Wesley, we got right here. Zach, you went down a little bit. Rex, right there. Carver. Who's Carver again? Huh? What Carver? Oh, fuck. Dude, did you have your hand raised the whole time? Okay. I was like, God, all right. That was the double points. Acceleration center of the disc.
Oh my God! God dang it!
No way, Walter. You didn't even know to look for the units? Walter even knew the units were going to be an issue. You even knew it.
I looked at it and I said, that looks right.
Yep. So units on acceleration are millimeters per second squared. I should have made it. You had to get at least 2 right, and you're still sitting at 1, right?
No,
The
I got
first.
2 right.
Oh, you did. All right. Good.
I jumped 18 spots.
Wesley back at the top. Zach, Carver, Rex, Jacob, still in there. All right, this is tight. This is so exciting. I should do this more often. I really should. Every time I do one of these, I was like, this is fun. All right. Next one here. Acceleration point A. Wow. Wow. Right? Spinning around like this, and all the omegas are constant, so the only thing you got is the centripetal acceleration, right? The centripetal acceleration, it's got that point A, it's got to be accelerating back towards the middle, right? It has to be accelerated back towards the middle. So it's just, so that's in the negative Z direction. It's headed back and accelerating back towards the center. I mean, this one makes me a little sad, right? That only 9. Like, what have I done? What have I done wrong here? Okay, let's see where we're sitting. Wesley's on fire. You got a fire next to yours too, right? And Zach right here, and then Carver right there, and then Rex and Jacob. All right, we got a double. You know what we're doing. You know where we're headed, right? This is it. This is the grand finale. Oh, wait, no, it's not the end. Oh, no, you got alpha the disc first. Yeah, we're not going there yet. Alpha the disc. You've only gotten one right. Oh. You just said, I heard you say that.
I may or may not be a last, Barry.
Oh no. Oh no. It's okay.
Showing up to class would help.
Yeah, that usually does. Yeah. Good job. Oh, thank you. Thank you for improving a little bit. All right.
Why?
What's that?
Why?
Why is it about that X? Yeah, it's the secondary crossed with the body, or the body is seen from the secondary. So it would be the secondary would be 2 crossed with 2 in the Y crossed with 10 in the K. And that'll get you about the I axis is what you would get with that. And then there's only 2 that had the I direction, right? But then the units were different. One was in radians per second, one was radians per second squared. So, right? It's weird. You got rotation about 2, but then you pick up an alpha about the other axis because of that cross product. Right? Okay. All right. Now this is the grand finale. Double points. Right. So we're sitting here. Wesley right up at the top. Zach right on your heels. Kyle, new to the game. Where you at, Kyle? There we go. Right up at the top. Right up there. Ben woke. That's what I said. Walk. Carver again. All right, here we go. You're gonna have to do a lot to catch up to Wesley and Zach. All right. Double points. What acceleration of point B?
What would you put as the answer? There's one person.
Well, look at that. I'm proud of you guys. Yeah, I'm proud of you guys. Right? There's a lot going on with that, right? How'd you guys do it? Did you calc it or did you just
How do you count that?
negative, negative, positive?
The only one with the sign.
Yeah, I'd buy that. Right? Isn't it? It's fun when you make these Kahoots because like I get to try to trick you and stuff, right? Like I use the numbers in different locations and then I units.
Well, B, so
You
going
did.
backwards. Like, there's no way it's not
There's
going
no way.
high.
There's no way.
Yeah,
Yeah. There's no way.
these idiots.
Oh, this is it. Here we go. Let's
I
go.
got 3 right.
Let's see where we're at here.
That's 30%.
Here's the podium. Third place. Kyle. Came in from behind there. Zach. Wesley, is this you?
70 points off.
Wesley. Runner up. Carver. Ben. Ben. Look at you. And then Carver right there. That's great. Right? It's weird that Walter wasn't on there. You want to play it again? That's the only one I got. I got one for coding too. Okay, that's it. That's all I have for you today. Like I said, I think that it saves who was here. Hopefully it does. Let me check really quick. Oh, where do I see that? View summary. View full report. Oh yeah. We don't want to share the screen to see how bad you were, right? You want to share? I'm not going to shame him. Oh wait, it's still recorded though.